So let's stop sharing. Yeah.
Okay, so I'll just wait maybe 1 more minute and then go ahead.
Mm-hmm.
Okay, so I think I'll start with an introduction. So yeah, thanks everyone very much for joining. I'm Jonathan Scarlett, and I'm an assistant professor in computer science and mathematics and one of the organization team at Institute of Data Science. So just to say a few words about IDS, in case you're not so familiar, we're a very interdisciplinary institute aiming to bring together researchers from all across NUS and beyond, particularly in areas relating to data science, such as computer science, maths, engineering, and business. And of course, particularly today, it's nice to see a lot of visitors from medicine. We have, we try to encourage collaborations, and we have several partnerships with agencies and industries in Singapore. Some of our main projects at the moment include the GRAB NUS AI Lab, and again relevant to today, the AI in Healthcare Grand Challenge, which is a major ongoing project. We also have a PhD program, and as you're probably aware, since we have these PhD workshops. So again, our PhD program is fairly interdisciplinary, and we started this type of workshop last year, where we basically aim to have our students share the knowledge they've accumulated. And we hope that our students will learn from these, and of course, the visitors will also learn from these, and that we can sort of promote some interactions with others having similar interests throughout the university. So yeah, with that, I think I can hand things over to the speakers, Hanae and Ronald. This one's a 2-day workshop. And yeah, basically the two of them will be in charge from here on. I might just be in occasionally to visit. But yeah, I think we can go ahead with Ronald.
Okay. Okay, so good morning, everyone. So first of all, thank you for joining our workshop titled Machine Learning for Healthcare, where we will talk about the implementation of machine learning models on healthcare data. And my colleague, Hanae, and I, Ronald, will be the host for this 2-day workshop. So a little bit about our background. So both of us are PhD students at Institute of Data Science, and my research focuses on the application of data science tools for healthcare, while Hanae's research focuses on computational genomics. Okay. So before continuing, Hanae wants to do a short survey so we can have a better picture of the audience. So please, Hanae.
Yes, good morning, everyone. Yeah, just before starting, we thought it could be nice to get a bit better idea of what your background is, maybe, and why do you attend this workshop, and whether you're already familiar with some programming that you experienced during your studies or your research. So I guess we are quite some people, so it would be take too much time to do a quick round, but is it possible maybe for each of you in the chat box to answer each of those three questions in order. Like, see, like, what's your background? Are you more focusing on biology, medicine, computer science, something else? Yeah, what's the motivation behind taking this workshop, and your experience with programming? Can you access the chat box area? Okay, I see some first answers. Can everyone please just quickly answer these questions? Just it will help us know you a bit better and adjust the workshop accordingly as well. Okay, thanks for first answers. Psychology, computer science. Nice. So from the first answers, we see that there are quite some diverse background. Nice. Nice. Okay, so thank you for starting answering. I guess, Ronald, you can proceed, and if you want to, if everyone can keep answering, that would be nice. Thank you.
Okay, so let's continue. So this is the agenda of our workshop. So basically, we'll teach the theories needed in the morning session, and you will have the chance to apply the models learned in the morning during the afternoon session. So for the first day today, during the morning session, I will give an overview of healthcare systems and also the fundamentals of machine learning for healthcare. And after that, Hanae will introduce three well-known machine learning algorithms, namely Logistic Regression, Support Vector Machine, and K-nearest neighbors. And next, in the afternoon session, I will introduce a little bit about healthcare dataset design process and also the dataset that we are going to use for the hands-on lab session. And after that, Hanae will guide you for implementing the three machine learning models on our dataset. And in the second day, during the morning session, Hanae will first introduce about neural network, and after that, I will cover some evaluation metrics that we can use to evaluate the machine learning models. And furthermore, I will also give an overview of some challenges of AI in healthcare. And lastly, in the afternoon session, Hanae will guide you for implementing neural network on the same dataset. And then after that, I will take over for evaluating all the four models, okay? So as I mentioned before, for this morning session, I'm going to introduce a little bit about healthcare systems and the fundamentals of machine learning for healthcare. And after that, Hanae will introduce with three common machine learning models called Logistic Regression, Support Vector Machine, and K-nearest neighbors. So first, let's start this session with introduction to healthcare systems. But along the way, if you have any questions, please feel free to ask through the chat box or even just speak up directly, okay? So let's start with the simple interaction at the heart of any healthcare systems. So what we want to do is to facilitate an interaction between two parties. On the one side, we have a group of people we call patients. So people who are sick, people who are injured, and maybe people who are healthy but want to get some preventive care. Or maybe people who would like to ask a question or get some information, or maybe people who have a concern about someone else they care about. And on the other side of our interaction, we have a group we call healthcare providers. So these are the people who can help the patients, doctors, nurses, pharmacists, lab technicians, so a pretty wide range of people. And also sometimes we also include institutions like a hospital or an imaging center. And sometimes it might make sense to include others, like, for example, makers of healthcare goods and services like a pharmaceutical company or a medical device maker. And the goal we have for this interaction between the patients and the providers is to have something that we call healthcare, which flow from the providers to the patients. So we want the patients to be able to get help when they are sick, and we want people to be able to get prevention when they can benefit from that. And we want people to be able to get their questions answered when that is what they need. So that is why we set up a healthcare system. So we set up a healthcare system in which we can get healthcare from the providers to the patients in an effective and hopefully in a timely way. And now we might be happy enough if we could stop there, but we cannot really stop there because we need something to go back in return, because the providers need to be able to get compensated in order to be willing to do this. Because if we do not pay them somehow, then providing healthcare will not be sustainable. We will end up with no healthcare providers, and that will be bad for our interaction. So we have to have a transaction here in which healthcare gets provided in return for some compensation. And you might think of these pictures as a map or a diagram of the interactions in a super simple healthcare system. And in fact, this is the way that healthcare systems work around the world, pretty much everywhere in the world for pretty much all of recorded human history. And this is basically how healthcare works, okay? And let's take a look at the group of providers and take note of the different kind of providers we find in there. So we can organize this into two groups. So first, the people, the medical professionals who provide care. And second, the organizations that are involved in providing care. So first is the people. So there are many different kinds of medical professionals in the healthcare system. So we start with physicians. So who are people who generally have a medical degree and play a central role in providing healthcare. So there are many different types of physicians varying along multiple dimensions. Sorry, let me check. Okay. So most physicians have focused training in a particular area of medicine and what we often call their specialty. And in fact, physicians are often referred to by their specialty. And we may refer to internists, for example, pediatricians or cardiologists or thoracic surgeons. And physicians work in a variety of settings. So many physicians work in what we call outpatient settings. And by outpatient, we generally mean outside of a hospital. So for example, in a physician office or clinic. So in outpatient care, patients come in, see a provider, get any consultation or treatment that they need, and then they go back home, generally all in the same day. And some physicians also even only work in inpatient settings. And by inpatient, we usually mean care provided to patients in hospital. So patients needing inpatient care will be admitted to the hospital, stay there for a period of time and receive care, and then go home when they are done. So physicians often work with other medical professionals. So our second group of people to take note of are those who commonly work with physicians to provide care. And nurses play an essential role in providing care. And nurse practitioners and physician assistants can play roles as well. And there are often technologies and people with skills and training to carry out particular medical procedures, drawing blood or operating imaging equipment, for example. And we often think of people in this group as working as part of a team with physicians to deliver medical care. So physicians may play a leadership role in planning and delivering care. And beyond medical professional, there are organizations that we need to look at, and we distinguish three types. First, physician practices. So we say physician practices are the organizations within which physicians work, providing the administrative and the physical infrastructure that they need to do their work. And we mainly think of practices as providing infrastructures for outpatient care, the rooms and equipment that physicians might need to see and treat patients coming in to see them. And practices often hire personnel like nurses or others like scheduling and billing personnel to work with physicians in the practice. And then second, we note hospitals. So hospitals are organizations that house facilities for providing generally more complex care for patients. So hospitals have beds where patients can stay and often house more complex equipment, facilities for surgeries, advanced testing and imaging and related things. And some hospitals also house facilities that can be used for outpatient care, like clinics or emergency departments. And hospitals also generally hire a range of medical professionals like nurses to provide care. And the third group is a set of independent organizations, by which we mean ones that provide facilities in which some types of medical care can be provided, but are not part of a physician practice or a hospital. So there are a wide variety of these. Laboratories, for example, perform diagnostic testing. Some labs are part of a hospital. And sometimes you will even find a lab as part of a physician practice. But others operate independently in the community. And they may receive referrals from a physician when a patient needs a test. And the patient can go there, get the test, and the lab will report the results back to the doctor. And finally, a note on the relationship between physicians and other organizations and facilities like hospital. One thing to be aware of is that in some systems, physicians or physician practices and facilities are often organized separately, though they work closely together. For example, for inpatient care, commonly a physician will provide medical care and the hospital will provide the facilities. And while they work together, they're considered technically separate entities by the healthcare system. They are paid and organized separately. But in other systems though, you might find them more closely integrated. For example, with the hospital employing physicians and thus providing both the facilities and the physician services in what is considered the same organization. And when we think about providers, a useful organizing principle is that there are levels of care. And this starts with the idea of primary care. So by primary care, we mean the initial care a patient might receive, the first and most generalized stop for a patient with a healthcare issue. So a place where a patient can bring a wide variety of issues they may have. So primary care providers are the ones who provide this. And they often provide treatment or guidance on a broad range of general conditions. And primary care providers can sort out situations that need referrals to more specialized physicians or other professionals. And they can often help patients coordinate care across multiple other providers or physicians they may be working with. So we might say primary care is a very basic backbone of healthcare provision. And primary care is often provided in outpatient settings. And it is usually provided by physicians who have specialties like general practice or family medicine. And at the next level, we encounter secondary care. So this is care for less common, more complex conditions that will benefit from management by providers who specialize in a particular conditions, a particular type of treatment, or maybe who specialize in a particular part of the body. So we often call physicians providing this kind of care specialists, though terminology can vary. For example, you might sometimes hear them called consultants. For example, cardiologists who focus on heart conditions, or endocrinologists who work on hormone systems, maybe focus on particular related diseases like diabetes, or maybe oncologists who specialize in treating cancer patients. So patients will commonly be referred from a primary care doctor to a specialist when that is needed, though sometimes patients will find their way on their own. So secondary care, like primary care, is often provided in outpatient settings. And an outpatient basis could be provided in a physician office or clinic. But as we get into secondary care, we also start to involve inpatient care more often. And when we start thinking about the kinds of hospital that can provide this level of service, we might first think about what might be called a local hospital or a district hospital, or maybe a community hospital, which provide a basic set of hospital services for patients who need secondary care. And the third level in our sequence here, tertiary care. So primary care, secondary care, and tertiary care. So this describes even more specialized care that uses more advanced and more complex treatments, like complex surgeries or other treatments that involve advanced technologies. So tertiary care is less commonly needed to the secondary care and way less commonly needed than primary care. So the tertiary care level is heavily associated with inpatient care, though it sometimes can happen in outpatient settings too. And we commonly think here about care provided by the most specialized physicians, often working in larger referral centers with the most advanced technologies and advanced capabilities. And they might be serving larger geographic areas and receiving referrals from a range of providers and hospitals around the area. And sometimes, in fact, systems explicitly organize their delivery structures to provide tertiary care on a regional level with a smaller number of larger, more advanced hospitals and clinics. So medical specialists set up to handle those services located in an area serving a broad geographic range. And there is one more level that sometimes come up, and of course we call it quaternary care, the fourth level. And this is basically an extension of tertiary care. And now if we are going to talk about this, then we will be talking about very advanced, sometimes experimental treatments that will require extreme specialization and care for patients with highly unusual conditions. And this will be generally associated with large advanced hospitals, often academic institutions, with very specialized medical professionals and other staff. Okay. So this general structure of care levels is a useful thing to keep in mind when thinking about the healthcare system. So now we have some common understanding about healthcare systems. And next, let's talk about some current challenges facing healthcare systems. Okay. So one important thing to note is just simply the fact that healthcare is very expensive. So healthcare costs are very high in many countries, and they just keep growing over time. And often when health economists or healthcare policy analysts want to think about this, they take a look at a measure of healthcare spending as a percentage of the gross domestic product or GDP. And when we look at this figure, what we understand is that pretty much all the countries in the world spend significant amounts on healthcare. And aside from the level, the trend can be worrisome because spending has kept going up steadily over time. So once we pay the bill one year, often we turn around in the next year and we need to pay a bill that is higher yet, which of course can make people a little stressed, right? So high and increasing costs prompt a lot of questions. And one of them is why there have been increases over time. So a lot of investigation has been done on this, and it highlights a range of different factors. So populations getting older for one thing, and for another thing, over the long course of the past several decades, populations' incomes and living standards have increased in many countries. And with that tends to come more healthcare use. And in some countries, it looks like price increases are part of the story. And by price increases, I mean increases in the amount of money we pay healthcare providers for any particular service. And if prices go up over time faster than inflation, even if we do not do any more healthcare, then our spending will go up too. So many observers have also focused in increases in technology and the capabilities of the healthcare system. And that often goes with increases in utilization. And those are an important part of the story of increasing costs. The specifics, of course, can vary from country to country, but this all suggests an important thing to keep in mind. So when we think about increases in technology and utilization, a chunk of the increase in healthcare spending that we see are associated with that. And with the arrival of new and often useful things we can do for patients, that can be a challenge. because high and rising spending has also posed important questions about value. Is the healthcare we are using worth it? Are the prices we are paying fair? So there's been a lot of discussions of these questions and more than we can get into here. But maybe it is enough to say that it is clear that there is a lot of really useful healthcare being delivered around the world. But at the same time, there are opportunities for making sure that we eliminate waste and work on improving value in most countries. And there's evidence that alongside the good things that are done, are also plenty of cases where we do things that look like they cost a lot, but may have limited benefits for health. And these are deep and complex questions for healthcare systems, and they present opportunities for improvements and opportunities for lots of discussions. So can we find ways to develop the kinds of medical interventions that steer us towards health improvements with good value? Or can we improve our delivery systems to get a better mix of services delivered efficiently? So healthcare system participants often end up right in the middle of this. So government can get pressure from their population to keep taxes down, for example. So they are often looking for ways to monitor costs, to manage costs, to make sure that they are providing the right tools and the right approaches. And healthcare providers, physicians, other professionals, hospitals also end up in the middle of this. So questions about healthcare spending, healthcare costs do not seem like they are going away anytime soon, but they are likely to continue to be a driver of our discussion and a driver of a need for innovation and ideas. And next, improving quality is a challenge that continues to drive conversations and discussion about healthcare system, but providing high quality can be difficult because healthcare is complicated, it is rapidly changing, we keep getting new therapies and new data and other new opportunities. And healthcare often involve multiple people who have to come together and work well together in order to provide care. And some things in healthcare have to be done quickly because it is a complex environment and getting it right can be a challenge. So many studies over time have looked at the quality of care provided in different healthcare systems, and often enough, they turn up opportunities to do better. And this can come in a variety of forms. So one of the frameworks used here notes 3 types of challenges. So underuse is one, doing or getting, but we do not get enough of. For example, one can sometimes find cases where relatively but beneficial preventive care was not used as widely as it could be or perhaps should be. And second, there could also be overuse. So there are services we think have some value for some patients at some times, but we may find ourselves in situations where they are overused, where they do not create value, or even sometimes where they can lead to problems. So for example, doing MRI scans for too many patients with low back pain is one example that has gotten some attention here. And then the third category in this framework is misuse. So making errors, using a treatment when it should not have been used, giving a patient a medication that interacted badly with another medicine the patient was taking, leading to problems maybe because someone was not keeping track well enough of all the medication that a patient was taking. So of course, healthcare providers and the healthcare system generally has many people in it that are highly motivated to improve use, suggest challenges, but then also suggest opportunities for improvement. And this generates pressure for providers because providers want to make sure they're providing high quality healthcare, doing everything they can to help their patients. And this has led to lots of efforts to monitor care, create data, create measurement tools, reporting tools, design better systems, or disseminate new information and so on, so that we can try to improve quality. And let's also take note of the challenge of providing access to care and access to coverage. So we can have a variety of issues here for a variety of reasons, and the specifics can vary from one country to another. In the US, for example, has had a history of not being able to get healthcare. so health insurance for its entire population, leaving some people without insurance, and which can make it difficult for them to get access to the care that they need. And there can be other access challenges too. Some come from socioeconomic disparities in access to care or use of care. And people with higher or lower incomes can have different abilities to access care, and it might depend on the healthcare system they are working in. And people with different levels of education may find it differently accessible too. And there can be cultural issues that can arise. There can be language barriers that come up. And sometimes access issues reflect a lack of providers. So we may not have all the physicians or all the hospitals in some areas that would make it easy for the population to get services. And some people may have to travel a long ways to find the provider they need, and that may make access difficult. So access challenges also suggest opportunities for improvement. So participants in the healthcare system are often interested in identifying approaches and tools and other things that can help with the access problem that we face. Okay. So after giving an overview about healthcare system, now I want to outline the reason why machine learning is needed to improve healthcare. So from our work so far, we can use ideas about the healthcare system to make a couple of observations relevant to machine learning and the data that might underlie machine learning work. But first, note that the wide variety of players in the healthcare system and the different roles they are playing. And it is important, and it can be really interesting to think about the different parts of the healthcare system and the different things they might want from machine learning, because they all have different roles. So providers, they are trying to provide healthcare to their patients, and they would like tools that can help with that. So they have to manage incoming information from patients. They have to sort that out into diagnosis and treatment plans. And they may have to assimilate data from colleagues or systems, getting lab results, imaging results, for example, and interpreting them. And they may also benefit if they can better identify patients who are likely to need services in the future and get on top of that early. And patients themselves may have interest in keeping themselves healthy, of course, and they may have interest in finding out whether or not they need medical care. And the list could go on, but the lesson maybe is not that complicated. If you are thinking about where to develop tools in this area, make sure you are thinking specifically about who in the healthcare system can use the tools and why they will be motivated to use them, okay? And a second thing to notice has to do with the data. So there are different entities here, and they have different kinds of data. And paying attention to who will have the data and why they have it can start to give you some insights. So providers, for example, often have data that comes from their work with patients. And there are lots of records from work with patients. They are kept these days in electronic systems that can be a really useful source of data. And some of this is kept in what we call electronic health records, or EHRs, and we call it EHR data. And this can be really useful, but it also has its own idiosyncrasies, of course, because its main purpose is to aid providers in working with patients, so may have a lot of discussion or explanation and text fields that are not always easy to handle. And you may have lots of details on diagnosis or lab tests, but it may have less on payments or other business matters. And it might be heavily regulated because there can be privacy concerns. And of course, there are many other sources of healthcare data, but remember, when you are thinking about data and you are thinking about the problems you would like to work on, it is really important to pay attention to the fact that the data are going to come from different sources and have been used for different reasons and have different issues, okay? So in the beginning, major areas that have driven the early application of machine learning in healthcare include enhancing and optimizing care delivery, improving information management, cognitive support for clinical care and predictions, early detection and risk assessment for individuals. And as mentioned before, the healthcare industry has been investing for years in technological solutions. including machine learning approaches, but mainly through rule-based traditional programming approaches with expert design applications that were typically focused on specific clinical areas or problems. But newer machine learning techniques offer the possibility of further improving performance and opening up new scalable solutions. And advancement of machine learning into all areas of medicine are now a reality, and they hold the potential to transform healthcare and open up a world of incredible promise for everybody. And one of the things that makes this technology so transformative in healthcare are the practically limitless applications. So everything from automated screening and diagnosis, adaptive clinical trials, operation research, global health, precision medicine, home health and wearables, genomic analysis, drug discovery and design, robotics, and many more. But of course, in order to successfully develop and deploy these systems into the healthcare domain and realize their full potential benefits, it is going to require everybody to have basic competency in both healthcare and machine learning concept and principle. Okay. So I have introduced some of the reasons why machine learning concepts of machine learning in healthcare. And let's start by addressing some obvious areas of confusion and overlap to the best that we can. So first, it is important to know that while the terms machine learning and AI are often used in interchangeable ways, but still both are two different terms in various cases. So on a broad level, we can differentiate AI and machine learning as AI is a bigger concept to create intelligent machines that can simulate human thinking capability and behavior, whereas machine learning is an application or subset of AI that allows machines to learn from data without being explicitly programmed. Okay. So artificial intelligence is a field of computer science which makes computer systems that can mimic human intelligence. So it is comprised of two words, artificial and intelligence, which means a human-made thinking power. And hence, we can define it as a technology using which we can create intelligent systems that can simulate human intelligence, okay? Whereas machine learning is about extracting knowledge from the data, and it can be defined as a subfield of artificial intelligence, which enables machine to learn from past data or experiences without being explicitly programmed. And it also refers to a family of statistical and mathematical modeling techniques that learn from the data. And again, not through explicit programming. So first, let's break down the part of the definitions that talks about learn from the data without explicit programming. And we will also add to this without using hypothesis-based assumptions. So what does this mean? So in other words, we want to take a moment here and help to find for you the key differences between a machine learning approach and other related approaches to data problem solving that you might be more familiar with. And while there is significant overlap, it is important to have a feel for the key differences in approach to data problem solving to differentiate machine learning, traditional biostatistics, and computer programming, okay? So let's start by contrasting a machine learning approach with the traditional biostatistical approach. So biostatistics typically uses a hypothesis-driven approach by performing statistical modeling on a sample of a larger data set that contains the population of interest and making various assumptions. And the goal is to learn insights from the data that can inform building models. So we define success as discovering insights about the population characteristics. But machine learning, in contrast, emphasizes evaluation of the model and finds success as whether or not a given model can achieve accurate output. And the goal is then more performance-based, and success is determined by the best performing model for the data. So let's use a hypothetical example. Suppose our goal is to identify patients in a population who will be admitted to the hospital in the next 12 months. So with a traditional biostatistic approach, we will use assumptions to build a statistical sample for our data, and then build a model with specified data elements that provide insight into why a patient will be likely to be admitted to the hospital in the next 12 months. So for example, a positive pregnancy test or a late stage cancer diagnosis. Then success to a biostatistician for this problem is to discover anything true in the data about a patient likely to be admitted that can be applied to making a prediction with a model, okay? But in contrast, a machine learning approach will be different. In that, we will define success differently and use, for example, previous claims data to build a model first, and then choose the model that produces the most reliable, accurate predictions. And the difference in the approach can be seen in how success is defined. So in this case, success is achieving a model that produces accurate predictions without explicitly defining the patient characteristics first to drive the model creation, okay? But what about the difference between machine learning and traditional approach for building a model? So in computer engineering or traditional programming, we will explicitly define in coding language exactly what information the computer needs to use at each step and what calculation to perform in order to obtain the expected outcome. So here again, we will be using explicit data to build an automated model. And in traditional programming, if we want to create a model that could automate the diagnosis of abdominal pain, then we would program the computer to follow a pre-described series of calculations based on decisions that the user or programmer chooses. So for example, we will write our programs so that important data points inform the output, such as where the pain is located, the presence of fever, and etc. So we design a value or even a decision tree for each possible input in a way that the necessary clinical knowledge is imparted in the program. And that given a new set of variables, the desired output, or in other words, the likely cause of abdominal pain will be reliably produced. And again, the key here is that programming and potential decisions are part of a manual effort to deliberately encode the steps or knowledge needed to provide the automated input. And in our example, if new data comes to the model from a patient with right lower quadrant pain with a fever, then we will expect that the program output will probably be appendicitis, okay? And now, what if we did not know how or when to use traditional programming to code all the different permutations and decisions that need to be considered with the input data to arrive at an accurate output? So, well, this is where we might call on machine learning. So, if traditional programming refers to a function that is written by a human programmer to solve a problem, machine learning models learn the functions from the examples of input and corresponding desired outputs. And when applied correctly, machine learning models can effectively learn all these components of a function that will have had to be coded by someone just by leveraging existing data. It can then produce reliable, repeatable predictions and decisions as output. And to use our example again, if we wanted to do the same task, in other words, automate the diagnosis of abdominal pain using clinical data. So if you wanted to use machine learning approach, the series of calculations or decisions will not need to be explicitly written by a computer programmer. And instead, this time programming, right lower quadrant pain and fever are suggestive of appendicitis. So we will need to pass the data into machine learning model that can accept the data variables and corresponding outcome diagnosis. And the model will use this data and outcomes or input-output pairs to learn the relationship between the data and the output label automatically. And it will learn to assign the proper values and calculations based on the data at a scene without needing a human to explicitly program rules to explain the relationship. And to put this another way, a dataset with the correct answer will be fed into the system in such a way that over time and many examples, the feedback leads to a model that learns the important features automatically and generates the desired output. And the end result or goal, an automated diagnosis of abdominal pain in this example, will appear the same, okay? And there are several advantages to machine learning models for model development over the traditional biostatistics or rule-based computer programming approach. So first, machine learning requires less people, less effort, and less time to learn the best model they can from the data. And another aspect of machine learning that stand out include the fact that extremely large data sets can be accommodated and learned, and perhaps beyond a human programmer or expert biostatistician capacity to process. And similar to biostatistics, there's also an opportunity to discover exactly which variables out of the many that are used as input are most important for the model's decision output. But it is just that this part of the process, it is not the main objective in machine learning like it is in traditional biostatistical analysis. And the important thing is just to recognize that a very big advantage of machine learning, broadly speaking, is that computer model can be created using data to identify important features and obviate the need for upfront, a priori data analysis or painstaking and time-consuming rule-based programming, okay? But of course, in spite of huge potential of machine learning, we should also acknowledge some of its disadvantages in comparison with the traditional biostatistics or rule-based computer programming approach. So first, machine learning often requires a lot of data to train on, and this should be inclusive or unbiased and of good quality. And sometimes we also need labels, but in healthcare, most of the time it is very expensive and difficult to obtain the labels. And second, machine learning needs enough time to let the models learn and develop enough to fulfill their purpose with a considerable amount of accuracy and relevancy. And it also needs massive resources to function, which can mean additional computing power. And we must also carefully choose the algorithms for our purpose. And lastly, machine learning is autonomous, but highly susceptible to errors. And suppose we train an algorithm with datasets that are small enough and not inclusive, then we'll end up with biased predictions coming from a biased training set. And this leads to low quality of predictions made by the models. And in the case of machine learning, such errors can go undetected for long periods of time. And when they do get noticed, it takes quite some time to recognize the source of the issue and even longer to correct it, okay? So now let's talk about different types of machine learning. So there are several types of machine learning algorithms, but let me introduce three main types of machine learning algorithms. So the first and the most basic type of machine learning algorithm is supervised learning, which is the one we are going to focus on this workshop. And this type of machine learning algorithm is trained on label data. So we call this supervised learning because we are supervising the algorithm, or in other words, we are giving the algorithm the right answer for a number of samples. And then we want the algorithm to learn the association between the inputs and the outputs and to sort of give us more of the right answer, okay? And the second type of machine learning algorithm is unsupervised learning. So speaking loosely, you are given a data set, but I'm not going to tell you what the right answer is on any of your data. I'm just going to give you a data set and I'm going to say, will you please find interesting structures in this data set? So that is the unsupervised learning problem, where you are sort of not given the right answer for everything, okay? And the last type of machine learning algorithm is reinforcement learning. So it directly takes inspiration from how human beings learn from data in their lives. And it features an algorithm that improves upon itself and learns from new situations using a trial and error method, where favorable outputs are encouraged or reinforced and non-favorable outputs are discouraged or punished. And the basic idea behind reinforcement learning algorithm is this idea of what is called a reward function. And what we have to think about is, imagine we are trying to train a dog. So every time our dog does something good, we say good dog, and we reward the dog with snacks, for example. And every time our dog does something bad, then we go bad dog, right? And hopefully over time, our dog will learn to do the right things to get more of the positive rewards and to get more of the good dogs and to get fewer of the bad dogs, okay? And since in this workshop, we are going to focus on supervised learning. So there are two tasks within supervised learning, which are classification and regression tasks. So the first one is classification task. So in a classification task, the variable we are trying to predict is discrete. So as one specific example, let's say we collect a data set on breast cancer tumors, and we want to learn the algorithm to predict whether or not a certain tumor is malignant. So malignant is the opposite of benign, right? So malignancy is the sort of harmful bad tumor. So we collect some number of features, some number of properties of these tumors. So let's say that we're going to look at the size of the tumor, and depending on the size of the tumor, we will try to figure out whether or not tumor is malignant or benign. And so the label is either 0 or 1. And so this is an example of a classification task where the variable we are trying to predict is a discrete value. It is either 0 or 1, okay? And some examples of the common classification algorithms include logistic regression, support vector machine, k-nearest neighbors, okay? And the second task is regression task. And the term regression sort of refers to the fact that the variable we are trying to predict is a continuous value and price. So the variable we are trying to predict is a continuous value, okay? So the regression algorithms attempt to estimate the mapping function from the input variables to numerical or continuous output variables. So for example, when provided with a data set about patients' health status, and we are asked to predict their length of stay in hospital, that is a regression task because length of stay is a continuous output, okay? And some examples of the common regression algorithms include linear regression, support vector regression, and regression trees, okay? So after learning some of the advantages, the common perspective is that machine learning is like a magic box that can somehow solve all of our problems. But we should know that while machine learning models may be appearing to be doing some magic trick that can learn a solution to any problem, it is really just the application of a mathematical formulations to a data problem. And all of this is framed in a way that is similar to how we view the human learning process, showing examples to teach a concept. But sometimes the model just does not learn the way we would hope. So here is an example of an X-ray machine learning model that was supposed to be able to detect pneumonia better than humans. But the model did terrible in a small clinical test. And when they looked into it further, they realized the machine learning model was learning the labels stated in the top right-hand side here, which usually contain information about the hospital name and also which site is represented to predict pneumonia. So why was it doing that? So, well, the model was given data from 2 hospital systems, one from an outpatient center with a 1% prevalence of pneumonia, and another one from a hospital setting with 100% prevalence of pneumonia. So in this case, all the machine learning model had to do was to determine which hospital the X-ray come from to decide whether there was pneumonia or not. So based on this example, at first sight, it is a seductive thought to look at machines and say they are logical and rational, and they do not play favorites, and they do not make irrational mistakes. But machine learning systems are very different because they are built on our own data, and oftentimes that data is flawed, biased, and certainly not inherently rational. And that drives home the point that these machine learning tools with many advantages also come with disadvantages that must be accounted for and mitigated by knowledgeable developers. And now that we are very seriously applying AI to medicine, we have to be careful to understand, recognize, and protect patients from the biases and errors that may arise from these systems, okay? And after all, we will need a lot of medical data to build our systems, and it is estimated that medical data doubles every 8 to 12 months. And basically, there is now more than ever sufficient data. But the better question is whether all of this data is actually usable for our machine learning systems. And the answer is not exactly, because medical data is messy. And it is generated often in a discontinuous timeline. that also suffers from missing due to lack of collection or documentation, and otherwise fragmented heterogeneous systems, since various electronic medical record systems that lack of interoperability are being used by healthcare providers nowadays. And further, unlike many other data types, there is also a distinct medical shelf life, because all the data are often less relevant, if not distracting, when predicting future events. But of course, currently, there are some machine learning methods that can be used to address some of these problems. But I just want to remind you that when we want to apply machine learning on healthcare data, these are some of the problems with the data set that we should be careful about, okay? So now we have briefly discussed some of the dangers of the oversimplified view of building a machine learning model. So just picking any data set or problem and throwing a magical machine learning tool at it is probably not the right choice. Instead, it is critically important to begin with an informed question. And this may be from the medical literature or pressing clinical questions, but you have to start with questions that include the detailed analysis of the output of your future model and the available actions. And especially in medicine, machine learning is best understood as a means to an end that has consequences. So without question, domain expertise and intuition brought by experience adds to the art of machine learning, but sometimes intuition is simply wrong and you have to revisit your assumptions. So finding the right questions and forming a machine learning solutions involve reinforcing the advantages and limitations of the different choices in the process. So this is the end of my session. So feel free to ask any question if you have. If you don't, then next, my colleague Hanae will discuss with you three well-known machine learning models, logistic regression, support vector machine, and k-nearest neighbors. But before that, I think we can take a break first for about, how about 7 minutes? So we will back at 5:10, okay? So yeah, we can take a break now. Thank you.
See you soon.
Yeah.
All right. It's 5 past 10. Is everyone back? Okay, so I hope everyone's back. We'll start so the second part of this morning session. Maybe first before starting, any question about the first part of the session after your break? No? Okay. So for the second part, feel free to ask any question when you have one by either unmuting yourself or through the chat box. Yes, and so also I noticed that there are quite some different backgrounds out here, some from more biological medicine, some more from computer science already with more background in already machine learning techniques, etc. So I hope it won't be like too fast for some people and too slow or too boring for others. So feel free really to stop me or raise questions. Okay, can you see my mouse also?
Yes, we can see
your mouse. Okay, thank you. Okay, so welcome back. Good morning again. And for the second part of session of the first morning session, so we'll focus and study more in details 3 classification models that are quite popular. So what we'll see today is first logistic regression. So we'll see later that despite the name, it's a classifier. Also super vector machines and K nearest neighbors. But keep in mind that it's 3 examples and there are a wide range of different classifiers out there. So I put a few other examples here, like naive bias, some decision trees. It's more like family of algorithm. Then you have like random forest, which is similar to decision trees, but with some randomness included, and so on and so on. So I cannot list them all. So, but we'll focus on 3 of them today. Okay, so before starting diving into the models, I just want to do a quick reminder of what Ronald introduced just before, so that machine learning has different types of different branches in machine learning. We'll focus here on supervised learning, so where we have observation data and target output variables. Like a pair of pairs as input, and in this supervised learning, there are 2 main tasks. So classification with discrete outputs. So for instance, like here's one example: you have expression of gene 1 and gene 2, and from this you want to determine, for instance, whether your patient is sick or healthy, and then you want to find a model that can draw a good decision boundary between the 2 classes. You have discrete outputs with 2 classes. You can have binary classification or multi-class classification with more than 2 classes. Or you can have regression where you have an expression of gene 1, and what you want to predict is the number of years, for instance, your patient are going to survive. So it's continuous variable. But in this workshop, we'll focus mostly on binary classification, only on binary classification. Okay. Now, I would like to introduce more details the machine learning setup, because it needs to be very clear in your mind. It's common for all supervised learning as machine learning problem solving. What you have, so as we discussed before, is a training dataset as input, which is a pair of an observation table or observation matrix X train in blue here, where you have, for instance, n training samples, like n, let's say n patients with k features described by k features, for instance, like their heart rate, heartbeat, their temperature, the type of medicine they are taking, etc. And as target variable, you have y train, which is what you want to predict. For instance, is the patient going to survive, or is the patient going to respond to the treatment, etc. That's a kind of example. So we have this training data set with those pairs. What we want to do in machine learning, we want to take a classifier model, because we're interested in classification. Take classifier model, which is a function, let's say f, that is parameterized. So it depends on some parameters, theta. And theta can be anything you want, basically. So you know the general shape of a model, f, but you don't know which parameter that are well suited to your problem. So the idea in machine learning is that you select a model architecture, and then you need to train the model. That is to say, to estimate good parameters, theta hat, that are well suited to your training data set by really like inferring, so updating the parameters depending on your data set. Once you're finished with that training step, you have a model with fixed, good estimated theta hat parameters. And what you want to do next is to take a new observation, so a testing data set, which is also a pair of observation table with new patients, let's say, that are described by the same exact features. So like M new patients, K same features. And you have also the corresponding output, target output, Y test. And from this, what you do is you apply directly your trained classifier, your trained model, on this new observation table in blue to get predicted labels. So give you an answer of like how long whether the patient will survive or not, for instance. And then you want to know whether your model can generalize well, because you train them on some training data set, but can it be also relevant for your new unseen testing data set? So then you use your Y test, your true labels, you compare it with your predicted labels using some score metric to evaluate how good your model can generalize. So that's the main framework of machine learning problem solving, right? So you need to keep that in mind. Okay, so once we introduce this, we can focus now on our first classification model, which is logistic regression. So what I plan to do here is first do a quick reminder on multiple linear regression, which is a regression model. So not a classification model, but it makes some sense here to compare it with logistic regression, as you will see. After that, we'll introduce the logistic model regression expression using sigmoid, and then focus on the model training, how we train this model. And we'll also discuss a little bit to go a bit further about regularization in logistic regression. Okay, so let's start with some reminder on multiple linear regression. So I guess linear regression, all of you will be very familiar with this concept. Multiple linear regression is the same. It's just that instead of trying to predict an input variable depending on one observation, you predict it based on a set of different variables, which is what we have here. We have an an observation table with many different features. So you have your training data set with your set of X and Y train, and you have a shape of a model. You want to estimate the parameters depending on your data. Oops. Okay. So in a linear regression model, basically the shape of the expression is like this. You must be very familiar with it. So basically you take some example, some sample, you multiply it by some weights, you give it some weight, so it's linear constant weights, and you can add some bias, basically. So you have two main parameters, and you try to estimate those parameters, W and B, the weights and the bias, right? So you try to train to estimate optimal model parameters, and to do that in multiple linear regression, a very common approach is to do least square estimation, okay? So let's take an example. You have one observation, so let's say one patient, X, described by K features. So you have to describe your patient, you encode him as a vector of dimension K, with, like, for instance, different clinical features, age, temperature, etc. And you want to predict the number of days of survival in ICU in intensive care unit, which is a real number, continuous. So here it's regression. So it's just like in one dimension, an example of how this could look like. You have a temperature, and here you have a predicted output in the y-axis. And the y hat is just the estimated. You have a model parameters we started introducing with the model weights, which here would be a vector of dimension K, because for each feature, for each different feature that describes the data, you will have a weight for each of them. And the bias term, which is just one term to correct for the bias, okay? So this was previously in the illustration one dimension. Let's try to visualize it multiple linear regression. So with two features in two dimensions, then the model you will try to find is the plane here that tries to fit as best as possible the observation data in red that you can see. So to minimize, basically, you want to minimize the distance between the plane and the different observation data in red, basically to minimize the length of the black lines that you see on the plots, right? And so if you consider the model equation in multiple dimensions, you will have to sum basically the observation for each feature and the weights corresponding to each feature and add the bias, right? So it can be written as a scalar product as this, okay? Okay, and so you have a shape of a model now, but you want to train it. So to determine which weights, which bias do we take? You cannot know them in advance, right? So you used least square estimation. So basically, the idea of least square estimation is to minimize the distance, as I said before, minimize the distance between the data you observe and the model. So this is just a mathematical formulation of this. Basically, the optimal W and B, the optimal weights and bias, so W star, B star, will be the ones that minimizes this expression, which is the sum of the distance between the observation and the prediction from the model. Okay, so then you can write it in a matrix format. And then you can demonstrate, you can adjust this formula to express W. So here actually my formula is a bit incomplete. This formula is actually the answer, the optimal W, the optimal weight. Once you have an optimal weight, you just have to plug this expression into your model formula to get the optimal bias term. So you have this mathematical expression that gives you the answer you want based on your data, on your pair, X and Y. What you see here is, first, good news. You can give an explicit solution to your problem. So you can really, it's a closed form solution, so you can express it as a mathematical formula. The drawback here, the challenge here is that it requires some matrix inversion. So here in this specific setting, the matrix we want to invert is inversible, so it exists, but it's not in practice so easy to compute. So here's the numerical challenge that you can have. Okay. Okay. So it's just some reminders about multiple linear regression. And now I would like to switch to logistic regression. So what we just saw is we're interested in regression, the number of days the patient will survive, for instance. So Y is continuous. Here now with logistic regression, we're interested in binary classification. So will the patient survive, for instance? Will the patient survive after 1 month in ICU? So it's a switch from linear regression to logistic regression. So the idea here, I want to give you some insight of a difference between logistic and linear regression. Let's say, as an example, a healthcare example, you have observation of tumors. For each patient, you can see different tumors. You want to see whether this tumor is malignant or benign. Let's say in one dimension, to be simple, you just look at the tumor size. In blue, it's malignant. In green, it's benign. So you have here the tumor size for linear regression, and the output is basically so 0, it's benign, and 1, it's malignant. So you can represent your data like the figure on the left, and doing a linear regression, then you'll try to look at, to find the optimal line that creates a boundary between both cases. Okay, so you can still do linear regression in this case, and then depending on the value, put a threshold, and then consider as the output 0 or 1. So you can switch from linear regression to some classification, right? But because here we're interested in logistic in a classification, you can see that, yeah, this line is will create very easily very high numbers or very negative numbers. So it's not very convenient. So what we'll do here in logistic regression is to apply some function on top of this line, on this linear line, to squeeze your this linear regression line into a probability function. So basically, here we apply a function, a sigmoid function, we'll see later, that gives a range, an output range between 0 and 1. And what you can see is that basically the output will be not so 0 or 1, but probability of a malignancy, close to 0. Very sure it's benign, and very close to 1, very sure it's malignant. That's motivation behind it, and that's why I wanted to do some parallel, some comparison between both models. So here in logistic regression, same setting as before, we have a training data set with pairs of X and Y. We have a model that we want to train. So logistic regression model, as you can see, is very close to linear regression. Main difference is that we will apply an extra function here that will like modify the line that we saw before. So it uses a sigmoid function to do that, right? And to estimate the parameters, then we'll see that it's not as easy as before. We cannot use a linear least square estimation. We will have to define an objective metric, so a cost function that we want to minimize. And then we will have to use some optimization algorithm to try to minimize this function in order to find the optimal parameters W and B. Metric. So the metric measures how far the predicted labels y hat are from the ground truth y, okay? So here we'll focus in this workshop on a very popular metric, which is the cross-entropy loss function. Other types of loss can exist. And the second item we need is optimization algorithm that iteratively updates the model parameters in order to minimize the metric, okay? And here we'll focus in this workshop on gradient descent, which is also a very popular algorithm. But keep in mind that many other types of algorithm can exist. It can be applied. Okay, so now let's look at the sigmoid function. So the sigmoid function that you first saw in some previous figures. So this is the expression of this function. So it takes any number, any real number, and it will basically, the idea is of a sigmoid is a squashing function that maps all like the line of real number into a range 0, 0, and 1. So it forces the input z, the input number z, to be a probability. Okay. Why this function? Actually, I mean, we could have thought of other functions that can squash the real line, like real numbers, into forces them to be a probability. The why a sigmoid is often taken is because it has a quite simple derivative. And you will see later that especially in neural networks, it could be very convenient because you'll need to compute a lot of derivatives. Okay, so that's the shape of a sigmoid function. You can see here. Oops, sorry. Okay. And now let's introduce the model. Basically, we have still the same model parameters that we saw before, a weight, one weight for each feature, and a bias term, W and B. And the model equation, basically, it gives you the probability of the item of a sample of a patient belonging to class 1, so for instance, having a malign tumor, depending, conditioned by the observation table X that you have. And the expression is like here. So it's exactly like a linear regression, but with a sigmoid function applied to it, right? So it's called logistic regression because it gives you as output a continuous number, because it's a probability. It can be any range between 0 and 1. Why do we consider its classifier? It's because in practice, we decide on some decision boundary threshold. So in binary classification by landscape, it's 0.5. So if the probability you have is above 0.5, you will classify your sample as malignant. If otherwise, you will classify it as 0 or benign. So the output prediction y hat is just just 1 or 0 depending on the probability. Okay. Before going further, I just wanted to give you some visualization of like the sigmoid and what a sigmoid model could look like in one dimension. So basically, if you change the weight W, it will have an impact on the steepness of the decision boundary. So the larger the weight is, the steepest the decision boundary will be. And B is the bias term, so it's an offset. It just shifts your function. Okay. Okay, so now that we saw the model shape, general shape, that depends on parameters W and B, let's focus on how we train the model. So we'll focus on this gray bottom side of the slide now, which is the two elements, the metric and the optimization algorithm that we need in order to estimate the parameters. Okay, so basically here we need to define one thing, which is the cross-entropy loss or negative log likelihood. So for one training sample, the negative log likelihood L is so minus log of the probability of y given x. And it can be written in the binary cases as it's shown below, because in the binary cases, so the probability follow a binary distribution. Oops, sorry, some formula got missed. Can edit that and send you back the slide. But basically, the idea is that you want to compute the loss between the predicted and ground truth, right? And then you have the cost function or objective function, which is defined as the loss function average over all samples. This is for one sample, and this is average across all samples. And this is defined as the cross-entropy cost function, J. That is the metric. And basically, finding the optimal parameters W and B will correspond to minimizing the expression of this cost function J. Okay. So this is some details about how you come with this expression, this definition of the cross-entropy loss. So basically here, the idea is that let's try to understand it conceptually. We want to find the optimal W and B, so W star, B star. So we want to maximize, to find the parameter W and B that maximize the probability of seeing the predicted output Y given the observation X, and also given the W and B, because you can choose whatever B and W you want. So it's called condition maximum likelihood estimation. You want to maximize this probability in the training data you are acquiring and observing. Basically here, what we do is we apply the logarithm function because it has some interesting properties. So we apply the logarithm function, and it will help us. It will help us changing the product into a sum, which is much more convenient for optimization. And then it's just convention taken in most books is to inverse the equation and to get the argmin of the negative log likelihood. And then you just define this expression inside the sum as the negative log likelihood or cross-entropy loss. That's the idea of where this definition comes from. Okay. So now that we got our metric, let's focus on the second part, which is the optimization algorithm. So first, why do we need an optimization algorithm after all? Like we saw in the linear regression, multiple linear regression, there was no real need for optimization algorithm. We just had the closed form solution, right? So our goal is to find here in logistic regression the optimal parameters W and B that minimizes the cost function J, which is the average negative log likelihood. Here, however, in this case, we don't have closed form solution, explicit solution. We cannot phrase it, unlike in linear regression. So what we need here is to do some numerical optimization in order to approximate the best parameters. Okay. So this is why we defined this cost function J. And what is very a convenient property in logistic regression that we'll use here, happy to have it here, is that in logistic regression, J is convex. So that means it has a unique global minimum. So convex function, for those who are not familiar with this concept, I just want to show you how it looks like. So here's an example of a convex function. The approximate definition would be that the second derivative is always positive. So it's basically, it has the shape of a ball. This means that if you find a minimum, it will be the global minimum. You cannot find the best one. While here, on the contrary, on the right side, you have an example of a non-convex function where the derivative is, the second derivative is not always positive everywhere. And here the thing is that it adds complexity to the resolution, as once you find a local minimum, you have no guarantee is the optimal one. So you can try to minimize your function and find some good parameters here, but actually here in blue it would have been much better, right? So it adds some difficulties to the problem. Here we are quite lucky, we are in more simple problem. Okay. So now let's explain how we are going to estimate those parameters in practice, which algorithm. So we are going to describe the gradient descent algorithm. Okay. I first show you how it works in one dimension, because it's easier to visualize and understand. So here the idea reminds you that we want to optimize, to find the best parameters, good estimate of the best parameters W star and B star by minimizing, which are the one that minimizes this expression, cost function J. So to do this, we are going to use the gradient, which is a mathematical operator. The idea of the gradient is that it's the vector that is pointing into the direction of greatest increase. Okay, so you have like, yeah, if you can visualize it, we will visualize it in the figure to be more easy to visualize. And here I take the example of gradient descent algorithm in one dimension with W only to estimate, no bias term. Okay, so just one parameter to estimate. First thing we need to do in gradient descent is to choose two hyperparameters, two parameters. We need to choose first a learning rate that we will call alpha, and a threshold, usually very smaller than 1, which is denoted epsilon. Then what we will do is, so we want to find the minimum of this J function here described here. What we'll do first is to do random initialization of W. So we take random parameter, okay, random W, and we see we have this value here, J of W, W0. Then what we'll do is compute the gradient of the loss, gradient of this function at this point. So the idea is to take the derivative here, which is the slope. So the local derivative of J at this point, and to move in the opposite direction of the greatest increase. So the gradient will be this direction, greatest increase. We'll move in the opposite direction. Here, oh, sorry. Oh, sorry, my side is not working. So basically we have a gradient here. We see that the slope is positive, okay? So the idea is to move in the opposite way because we want to minimize. So we'll move in the negative direction. So we'll move this way on the left side, right? And we'll update the weight with update the weight, and the magnitude will be weighted by the learning rate alpha. So here's the update function. You take your W0 and you move in the opposite direction with the magnitude weighted by learning rate. And you repeat this step until convergence. So if you follow my mouse, basically, next step you will fall here and maybe there, because it's still like the slope is still in the same direction. So you still keep moving left, right? And maybe at one point you will fall very close to W, to optimal W here, W star, that you don't have this ground truth value. And if the distance between W star and your W, I don't know, 12, like the 12th iteration, is below your threshold epsilon, then you'll stop. Because you don't know the optimal value, right? So you can keep on updating your weight. But you want to stop when you find that the increase, the change in the weight W is not so different. You're in a stagnation mode, basically. Okay. Ah, it works. Sorry. So basically, yeah. So let's do it again. We take a random W0 here. We have a slope. We update. We move in the opposite direction. So left in the weight. So the weight is the magnitude of the move is weighted by alpha, learning rate. Does it work? No, it doesn't work. Sorry, I give you the slide with the full steps later. Okay. Don't know what's working. Sorry for that. So you can move like this, move like that. Okay, move. You see that the more at the bottom of the ball you are, the smaller will be the improvements because the derivative will be much lower. So your update range will be lower, right? Yes. And then after a couple iteration, you have the update is not, is almost the same. You're almost always on the same point. It's the difference is lower than your threshold epsilon, so you stop there. And you don't have the optimal one, but you have a very close estimate. You can expect to have a close estimate. Then, so in 2 dimensions, it's the same idea. So here you have one feature, let's say, but you want to optimize both W and B. So it's just to give you an overview of what it looks like. So it was in 2D, it will look function like this with a convex function like this. And your goal will be to estimate the parameters that are really like closest as possible to the blue one, to the optimal ones, okay? So now maybe we found a way, an algorithm of steps to find some good estimates of W and D, but how to choose the learning rate alpha? It's a bit like theoretical, right? You find the learning rate, but which one to take? 1, 0, 1, 0, 0, 1, 10, we don't know. So the problem of choosing the right learning rate is really a big problem, because if you take a too high learning rate, as you can see in this first illustrative figure, basically you will see in your optimization a lot of zigzag pattern, because your magnitude of change of update, weight update will be too high. So basically you will see your function, you'll go to one side of the ball, the other side, etc. without even, and you can wait a very long time before falling in close to the right parameter in blue that you're looking at. And on the other side, if you take a learning rate alpha, which is too slow, then it can lead into a very, very long compute time. So then it depends on your problem, but sometimes you can be very limited because it's really taking forever to update. And in our case of logistic regression, as we mentioned, it's easier because we are in a convex, our metric, our cost function is convex. So at least it's just that we're going to be very slow. But in case of non-convex, in non-convex cases, basically the other issue that can arise is that if it's too slow, then you can get very easily stuck into a local minima, because you are close to the local minima, but you cannot, with the amplitude of your learning rate, you cannot go beyond it and fall into the global minima. So that's another problem. So, and what can be done also, so we could try it also in the hands-on session, is to do an adaptive learning rate. So because you can think maybe the first parameter, the first trial that you'll take, the first W0, first iteration, you can be very far from your global minima, as it's completely random. So you can expect, okay, it's far, so I can do a high step of learning rate. But maybe after a couple iterations, you can be a bit closer, and then you can reduce your learning rate step by step, so that you're more precise at the end of your training. That's the idea of, and the big issues behind the learning rate. Okay. So here's to go further. Okay, so to go further, I just wanted to mention, maybe for those who are already familiar with gradient descent, it can be more interested, and for those who, for them, it's already very new gradient descent, you can skip that. But basically, the idea in gradient descent, you have several variants. And the idea will be the same. You have still to choose the learning rate alpha, the threshold epsilon. You have a random initialization of your weights, of your parameters. And every step of the way, you will compute the gradient of the loss at this point in order to know in which direction to update your parameter. So here on the left is the classic gradient descent that we just saw, where you compute the loss after iterating over all training examples. So because it's the definition of our loss, it's the mean, it's the average of the loss over each training example. So you need to compute the loss for each sample, okay? So then you move in the opposite direction, you repeat until convergence. The drawback of this first more classical version is that it can be quite slow, especially when you have a very, very large training data set. It can be also a bit pain, like with your memory, etc., because you need to compute loss for each training sample. So to overcome this, there are some variants that are quite used in practice. The first one is stochastic gradient descent. The small update that with small changes that we do here is that instead of computing the loss after iterating over all the data set, we compute it after each training sample that we take in random order. So we take one sample, we compute the gradient, and we update, etc., etc. The advantage of this is that it's much faster, but it can result in also in zigzag patterns, because if you fall, let's say you have one like outlier, or you have like one sample which is very different, then you will move like in completely the opposite. You will have to update your parameter drastically. And then if you get more like a classical sample, then you will have to go back to what your parameter was. So it can result in a lot of hesitation during the training. So a compromise for this is mini batch gradient descent. So here the idea is to compute the loss, but on mini batches, which is a group of m samples. So it's like a compromise between both variation. And you select the samples and the order of the batches in random order, right? And you define this cost here, which depends average over the m samples, right? And the advantages of this is that you have more computational efficiency compared to the first classic version. And then you have less zigzag patterns. And one advice could be also to carefully choose your batch size, m. Usually we try to use it as a power of 2, depending on your available computing resources. Okay, so here's again an overview of the training process in logistic regression. Does anyone has any question on this? Any question on the model shape, the training, the metric? Something you were already quite aware of? No questions? All right. All right. So a last point in the logistic regression I wanted to talk to you about is the regularization. Because what happens is logistic regression is that you can quite easily have some overfitting issues. Because you really try to find the parameters, W and B, the weights and the bias that are well suited to your training data set. But it's not your end goal. Your end goal is that your model will have to be very good at generalizing on new unseen samples. And sometimes you train your model and it's super frequent that you end up with a model that is performs super good on your training data set. Like it's the loss, you can minimize the loss very well, but then on unseen data set cannot generalize so well, right? It's called overfitting issue. And in logistic regression, it often comes, when you overfit, it often comes with very large W parameter, basically. So that means if you, here I put you again the an overview of a figure of the sigmoid, the model shape in one dimension. That means that for one feature, the decision like threshold will be super steep when you have a very high W parameter, right? So then you were like super sure on this data set, this is the decision boundary. But maybe on unseen data set, you need to be to have a bit more like relaxation of a parameter. So to do this, there is a method called regularization that you can add to your logistic regression model. Basically, it's to add a regularization term, R, which is a function of W, of a weight, that is added to the cost function, J of W, to penalize large magnitude W's, large magnitude weights, and also to penalize the number of parameters. So maybe if you have a lot of features, it can force us, basically this regularization term will force us some parameters, some features that are not very needed for to predict the output to be set to 0 or almost 0, okay? And then you came with a new expression, a new cost function to minimize, which is just the addition of the negative log likelihood loss, and this new regularization parameter that depends also on an alpha parameter that you can change to regularize more or less, right? So the stronger the alpha is, like if you choose like for instance 10 is like a strong regularization, the stronger the effect of the regularization will be. But also if it's too high, if you regularize too much, then you will prevent your model of fitting your data, fitting enough your data, which is called underfitting. Ronald will introduce a bit more those notions later, but basically you need to find a good trade-off. And then, so this R term, this regularization term called R, what is its expression? There are different kind of type of regularization you can take. Two very popular ones are ridge or L2 regularization and lasso or L1. So ridge or L2 is because it uses the L2 norm, which is basically the Euclidean distance. So it's easy to optimize because of a simple derivative. And so it's quite used in practice. And the second one is the lasso or L1 regularization, because it uses the L1 norm, which is the Manhattan distance. So it's a bit harder to, so basically the Manhattan distance took the absolute value of your parameter. And it's a bit harder to optimize because the derivative of this term absolute value of the term is not continuous at 0. So it's in practice, in implementation, it's a bit harder to compute. But it's popular. Okay. And that's it for logistic regression. So what I wanted to end it with is the pros and the cons. Basically, logistic regression, the advantages is that in many, many cases, especially in healthcare datasets, it's sufficient to solve your problem in binary classification. It's quite fast and simple. And the loss function is convex, as we saw. And it's also quite interpretable because, as I hope you could see, it's quite close to the linear regression. Basically, you have features, you put weights on them, and then you just add the sigmoid function to force your observation to your expression to be a probability. And the cons on this, the drawbacks, is that it's basically a linear model up before the sigmoid layer. So sometimes in some data sets, you need some non-linear combination of the features in order to predict well your output. And let's think of an example. For instance, you want to predict whether a patient is obese or not. If you have like the height of a patient and the weight of a patient, basically you would like maybe to combine those features using like some ratio or some product of the features to get like some expression of a BMI, which is a good predictor of obesity, for instance. And this will not be possible with sigmoid logistic regression. And also another drawback is that it cannot directly handle categorical features because it requires as an input, so numbers basically. So if you have categorical features, let's say basically the color of your eyes, like is this brown, blue, or green, you cannot feed that directly into the model. You need to do that is called some encoding, for instance, one-hot encoding, in order to pass it to the model. Okay. So that's what I thought of. And that's it for logistic regression. It was a bit long because we had to introduce a lot of concepts, but it will be useful for other models and for tomorrow for the neural network models. Do you have any questions on this first model? No questions? All right. So let's jump to the second model that we will study today, which is supervector machines. So I'll first give you some principal intuition on how it works. Then we'll introduce the optimization problem that it requires to solve. And then we'll introduce the problem in the challenge in supervector machines of non-linearly separable data sets, and two possible solutions for it, which one is slack variables and the other one is using kernels. Okay. Maybe before starting, has anyone already like used SVMs for their research or during their studies to solve some question? Anyone familiar with it? No, not really. Okay. So feel free to ask any question. So first thing is, let's consider these data sets. Okay, so we have two features, feature 1, feature 2. So you can imagine whatever you like some gene expression, some clinical variable temperature, think of like height, age, etc. And you have different patients, for instance, which are represented by those dots. And you have, so the color stands for the labels, blue or green, right? Like sick or healthy, for instance. How would you classify this data? Any idea? How, like, visually could you could you separate those two set of patients? No idea? Okay, so I'll propose you something. Yeah, it's green versus blue, but yeah, draw a line, exactly. That's exactly what I was thinking of. So we can draw a line to separate green versus blue, indeed. So this is an example, right? It does the job, okay? Now, we can also think of this one, right? It also solves the problem. Actually, we can think of a lot of different lines. They all work here, right? So that's why here, because we want to find one good model, and there are a lot of them possible, let's try to define an important concept in supervector machines, which is the margin. So basically, the margin is the width of a boundary that can be, that we can increase before reaching one data point. So here we have this example of line, and the gray shadow is the margin, because it's it just hurts one blue data point. So we have to stop there, right? So we have a margin, which is a security bound between the two classes, two separation. Okay. And so among the possible sets of decision boundaries that we will see just after can be called hyperplanes, basically the intuition of linear supervector machine is to choose one decision boundary that maximizes the margin. So which is the distance from the closest point to the hyperplane. So for instance, here I try to draw the optimal one with a much higher, larger margin. The larger I could try to draw. Okay, and so this is linear SVM. Okay. So now just some math about hyperplanes. Basically, hyperplanes, quick definition, hyperplane is when you have a data set in dimension p dimensions, p features. Hyperplane is a fine subspace of dimension p minus 1. Okay, and the general equation of this hyperplane is given by this. Okay, so you have coefficients beta, and basically, yeah, I could have tried to make you guess, but in dimension 2, as we saw before, you could see that. So we have we have the data set, which is a plane, and then the hyperplane is a line because it's dimension 1. And in dimension 3, in a 3-dimensional subspace, then the hyperplane will be a plane, and etc. etc. Then it's a bit harder to visualize. And let's just note that when the beta 0 coefficient here equals 0, that means that the hyperplane, so the plane, the line, the hyperplane, goes through the origin of your data set. That's the idea. Okay, so just some representation. R2, the plane, then it's the line that separates both sets, and hyperplane in 3 dimensions, it's a plane. Okay. And then from this, as you saw, we try to define the margin, and to define the margin, we need to measure how far the data points, the patients, are from this hyperplane, this decision boundary. So to do that, we will use normal vector. So a normal vector basically is in this shape. and it points in the direction orthogonal to the surface of the hyperplane. Okay. So in 2 dimensions, let's focus on 2 dimensions. So some recall of a norm of the decision of a vector, right? Then when you have when you do the scalar product, basically between W, when you do the metric product between W and your data set X, and it goes to 0, that's basically, so if you have your decision boundary in black here, then you have the normal vector will be here, right? And basically that means that W transpose of W multiplied by X will be equal to 0, right? And then when you have, so it's a black one, and then you have in blue and in green, transpose of W multiplied by X equal 1. Basically, it just shifts the decision boundary. So, and on the left or right side or left side, right? And basically, so you can shift them until you hit a data point. And those, once you hit a data point, you can call those vectors support vectors. Okay. So now we have some idea of visually of what we want to do. We want to draw a line that maximizes the margin, right? Then we need to phrase it into some formula that we can then work on. So basically, we want to find the vector of with parameters beta, where so this vector will be a separating hyperplane. That means that if we compute this vector for all the blue data points, for instance, if we have the result of this function will be, of this model will be above 0, and for the green data point, for instance, will be below 0. So it creates a decision with a maximum merging. So basically, in other terms, we have a constrained optimization problem. We want to maximize the margin M subject to, so first one is more like some normalization issue. Main point is second point, where you want, basically, sorry, I cannot see. So where you want all your data points on one side or on the other side of the plane, right? And then you have, so the margin, we can be defined as 2 divided by the norm of your vector W, right? And 2 because you have it's symmetric with both sides. Okay, so in dimension 2, beta is W and B, weight and bias, right? And so you want to maximize this. So I just rewrote things in 2 dimensions. And basically the idea here is that when we want to maximize the margin, basically it comes with, it's equivalent to say that we want to minimize W. What we see here is that basically we have, for each data point, we have one constraint because we want it to be either on this side of the plane or that side of the plane. So if we have an data set with n training point, then you have n constraints. Okay, and this general shape of problem is called quadratic problem. And so it's a general like class of mathematical optimization problem. And basically here, there are some efficient global solution algorithms that exist to solve that. So I'm not going to the details here, but just to see like what is the kind of mathematical problem we need to solve, and that there are algorithms to solve those problems. Okay, so now we just saw previously kind of a simple example, right? Because we could quite easily draw a line to separate the green and the blue points. However, how do we do when the data is not as simple? Like the data is not linearly separable. So for instance, when you look here, there are two samples that prevent you from drawing a line that perfectly separates both classes. So how do we cope with this kind of setting? You have two main solutions. One is to slack variables. Basically, it's to allow a few points to be in the wrong side of the plane of a data set, right? And so your performance on your training data set will be not perfect, but maybe you can expect that it will be able to generalize well on unseen new data. The second one is to apply kernels. So this is a bit more tricky. Basically, the idea is a bit drawn here in the figure to put your input space where your data is not linearly separable, but to map the data into a higher dimensional feature space where the data would be linearly separable. And then you do SVM here in this new feature subspace, SVM, the super vector machine. So we'll introduce both kind of solutions, and you can note then in practice, you can also combine both solutions, 1 and 2. So first solution is to slack variables. So in the non-linearly separable case, what you can do is to relax on the constraints that we expressed before by allowing some misclassified samples. So basically, instead of having like this sample should be on this side, you can allow some epsilon, that you can allow some misclassified samples. It's also illustrated here in this figure. And then you can, you will add a trade-off parameter C into the optimization problem. So basically now you have a new optimization problem you want to solve, where you want to minimize W, the norm of W. And also you want to minimize the misclassified samples, but you can allow some, right? So it creates some soft margin SVM. And now you have more constraints, okay? You have 2 n constraints, but it's still a QP, sorry, a quadratic programming problem. So that's the first solution. The second solution, as tried first to give you some instinct of it, some intuition, is to map the data into a higher dimensional feature space. So where it will be linearly separable and run a super vector machine there. So for instance, here I took an example, quite simple example. You have 1 dimension, X. It's not linearly separable, like you cannot put, so here you have a data set is 1 dimension. So basically the hyperplane will be 0 dimension, so just 1 real number, a threshold, okay? But you can cut here or you can cut there. I mean, you won't have a good separation. It's not linearly separable. So, but what you can do is to create, to modify your data set, to add a new feature, x squared, and to represent your data like this, right? Oh, sorry. Then, sorry, it's not shown here, but you can draw here a line that can linearly separate both classes, okay? And then, so maybe what you can see here is that this line, so simple linear SVM here in this higher dimensional feature space, if you try to transcribe it back here on the original data set, it will basically create a non-linear decision boundary, like some circle, for instance, some polynomial separation, for instance, right? So here's just another example into 2D to 3D. So here you cannot find any line that separates both classes. By adding a third feature, which is a nonlinear combination of both, then you can draw a plane that can separate both classes. And if you try to express this plane back to the original dataset space, it will result in a nonlinear like circle, like nonlinear decision boundary. Okay. So the issue with kernels is like, actually first in practice is like, which kernel do you choose? Because there are so many kernels that you can think of. And it's hard to visualize whether it's doing a good separation in the feature space or not. Because here, for examples, I put very low dimensional examples. But in practice, you already have in your data set maybe 100 or more features. And if the linear SVM does not perform well, you want to try to add a kernel to it. But then that means that you have already a high dimensional data X, and you want to map it into a much higher dimensional subspace phi of X. So it's very hard then to visualize, right? So how do you represent it? And also the problem is also in terms of like quadratic programming problem. The more dimensionals you have, the higher it is to learn your decision boundary W, right? One, not solution, but one like good thing you can think of is to use what is called linearly separable kernels. Basically, this is a kind of a definition. Basically, this will help in computing because you can apply it to X and Y separately, basically. So this can help in the resolution. So I just introduced you before a few examples of what kernel you could think of. In practice, here are a list, not an exhaustive list of kernels you can use and that are quite popular. Many other exist, and it's often quite tricky to find a good one. Okay. So to end with, the pros and the cons of super vector machines. So the pros is that it can be nonlinear classifier when you apply kernels, when you do slack variables. It can help you to solve problems, machine learning problems, where your data is not linearly separable, which is not so possible with logistic regression. It is very well studied because it used to be state-of-the-art classification model in machine learning until 2010. Before that, it was like all SVM everywhere. So you have good like documentation about the background, the proof, it's well like understood. Pretty fast to train, actually, I'm not so sure about it. This can be quite slow, actually. And with quality programming, you can find some global optimal. The cons, however, is that it's very sensitive to outliers, because as you can maybe imagine, is that basically your decision boundary depends really on one or two data points. So then when you have outliers, it can really mess up the learning. And it's also, as I starting mentioning, it's also hard to find the right kernel. And when, maybe that's it. When you use kernels, then it can be very, very long to compute. And yeah, and one drawback is that also now those nonlinear SVM is not state of the art anymore in terms of performance. Okay, so that's it for SVM, super vector machines, which is the second model that we saw today. Is there any question you want to raise? You can also so either unmute yourself or put it in the chat box. No questions? So far, so good? All right. So let's finish this lecture by speaking about the third and last model, classification model that we'll see here, which is K nearest neighbors. So it's a quite simple algorithm, quite intuitive. And so here I will introduce you to the principle of this algorithm, the algorithm itself, and then how to choose the parameter K, the K nearest neighbors, how to choose this parameter. Okay, so principle and intuition first. This K nearest neighbor, so it's called the non-parametric classifier. And the idea is that you classify each test object or query, or you can call the test object query like new patient, for instance, based on its nearest neighbors. Which means that the training objects that are the most similar to it. So here I put back the same data set example training data set as before, with two classes, blue and green dots, two features. Okay. So here the idea is let's imagine you have two test samples to classify. Okay, new samples. What label, what predicted output would you give them? Any idea how you could proceed? In a quite like intuitive way. For instance, the top one, would you classify it more like as a blue example or as a green example? Yes, exactly. More like a blue example. Why would you? What motivated your choice? Yeah, actually, exactly. So there are some points nearby that are blue. So you could expect this one to be blue as well, right? because it's closer. Same here, we could maybe expect this one to be green as its neighbor points are green. So this is like the intuition, but now how do you measure that? Because what does closer point mean basically? So I guess more intuitively, what you first thought of is like the Euclidean distance. You measure the Euclidean distance between 2 points, and you see which ones have the smallest Euclidean distance. But you can actually think of different distances or similarity metrics that can be more suited depending on the problem you have. So basically, k-nearest neighbor stores all available cases and classifies new cases based on the similarity measure or distance function. That's the main principle of k-nearest neighbor. So this, beyond the Euclidean distance, what other distance you can think of is Manhattan distance. So it's some representation of how you compute it. And you have, for instance, you can have cosine similarity, which this one, so it's a similarity, not a distance, which means that the higher the similarity is, the closest the points are from one another. While the higher the distance is, the farther they are from one another. And cosine similarity can actually be quite useful when you're not interested in the amplitude of how far in amplitude the points are, but maybe the angle, like are they in the same angle or not, in the direction. So here for visualization, we'll use Euclidean distance, which is much more intuitive. And what do you require? What is required for the algorithm? It requires a distance or a distance metric. So let's say Euclidean distance and a parameter k, which is the number of neighbors that you will consider to classify your new test example. So given a new point test X test, let's compute the distance to all training instances. So here we have one new example here in white, and let's put k equal 3, so 3 neighbors. So you can compute the distance with all of them, and you can find that basically those three green dots are actually the closest ones, the ones with the smallest Euclidean distance. And then what you do is majority vote, which is assigning to X test the most common class among the nearest neighbors. So here it's quite not a lot of hesitation because they are all green. So you can classify it as a green example. New example. Up, you compute the distance. You see that those 3 samples are actually the closest ones. And 2 out of 3 are blue. So the majority is vote ends up with a blue point here. Okay. So as you see, quite intuitive, right? But one thing we need to choose to parameter is k, the number of nearest neighbors. Because basically, if k is too small, it will be very sensitive to noisy points. So here I put you an example of a binary Canon classification using 1 k equals 1, so one only the closest neighbor to classify the new sample. And if k is too large, then it can underfit like include too many points that are misclassified, right? So if you have k equal 1, k equal 5, it's a bit less, the decision boundary is a bit less less noisy. But then k equal 25, equal 25, then it's almost like a straight line, right? And it does not allow a lot of, some misclassified points. So how to choose k? As a rule of thumb, you can try a k to be to set k inferior of the square root of n, where n is your number of training example. It's like a rule of thumb. And also one advice that you can take into account is that usually it's better to choose a k which is odd, because you use majority voting. So if you have an odd binary classification and an odd number, then you have no problem with majority voting. And then, how to choose k? What you can do is to do some tests where you set different values of k, and you look at the performance of your model depending on the number of numbers you're taking into account. And maybe when you look at some elbow like this in your plot, that can give you a good compromise, a good trade-off for k. So now, pros and cons. So as you could see, KNN, k-nearest neighbors, is a very simple algorithm. It's quite generic, so does not require a lot of extra tool, a lot of like optimization, numerical optimization, etc. It runs as long as distance or similarity metrics exists, so it's okay. Also, you have no training time, because you have, as we saw when we saw the steps of the algorithm, you have your data set, you put a new sample, and you look, depending on this new sample, you look at the distances. You don't have to fit some parameters, etc. And what it can do, what is quite an advantage of this technique, is that it can produce arbitrarily shaped decision boundaries. So not like linear or not like incurved. It's really based on the data you have. So it can have some more fancy or more original decision boundary shape. And it has surprisingly good performance in practice, actually. The cons of this technique is that finding the neighbors at test time may be very slow. So then it also depends on the number of training samples you have, but you need to compute the distance with each of the training samples. So if you have several, I don't know, millions of examples, it can take a while. And also, so yeah, it also depends on the training samples, and it depends also on the number of features you have. But basically, the complexity can be quite problematic when you compute the distances. And then another problem, which can really make sense in medical data sets, is that you need to store all the training sets to be able to use this model for a new testing set. So basically, let's imagine you have a model that predicts well whether a patient will survive to a treatment or die. It can be very useful for clinicians, for practitioners, for medical doctors to make some decisions about the treatment. But then the thing is that, you developed your own model, you want to share it with a collaborator, but basically you need to give them access to your training set. And with medical data, you can have a lot of privacy issues with that. So it can be a problem. And also when your data set is huge, it's also, it's not a light model to share. And another problem with KNN, another drawback, is that the features are very sensitive to, the performance can be very sensitive to normalization. So you need basically your features to get the same weight before you compute your distances. As you see, because you compute the distances, so you assume that the weights are between the different features are well balanced. That's the idea. That's it for KNN. Yes, and to end with, I wanted to just, as a conclusion, have some pros and cons table with the 3 different models, classification models that we saw today. Yes, and 3 illustration of how it works. So basically, if I do some reminder, logistic regression, it's quite simple to interpret, simple to deploy. The shape of the model is quite simple. It's enough for most problems you will have to solve in practice, but it can be very bad if you don't do feature engineering, because if you don't do good assembly of the features before, if you don't study your features before, because it requires your data to be linearly separable, basically. So if you don't do any feature engineering, either it will perform bad, or you're very lucky, you have a good linearly separable data. Then supervector machine, it's well studied. It can be applied in either linear or nonlinear data cases using kernels. And it usually gives good performance. The drawbacks in practice is that it's not easy to find a good kernel. It can be quite slow to train when you add kernels. And it's sensitive to outliers. And finally, k-nearest neighbors. So it's easy to understand visually, conceptually. It's simple to deploy. You don't even need to use some fancy optimization algorithm. It can be put into production. So at least, I don't know now, but at least it's still the case, but previously, at least YouTube used it, KNNs, for their recommendation algorithm. And the drawbacks, however, is that it requires to have your data set in memory, locally stored in your computer, for instance. It requires to have a data set shared with the collaborators who wants to use it. And it's sensitive to normalization. Yes. That's it for me for the presentation of 3 different classification models. Hope it was useful for you. Do you have any questions you want to raise? Okay. If no question, also if you have questions on first part of the morning session, feel free. Meanwhile, you think of possible questions Okay, having dataset in memory means that computation cost is higher. I mean, it's higher computation cost for inference, so to get the prediction. The idea is that, for instance, for logistic regression or SVM, it's quite tricky, it's quite hard, as you could see, that it's quite hard to find the good parameters for those models. You need to do a lot of computations for training. But once you get the parameters, you store it, you know the parameters, you wrote it down, it's stored in your model. And then for inference, it will be quite fast. You just have to compute, to take a new sample and to pass it to your function. While here in KNN, for each new sample, you need to recompute all the distances to find the minimum, the smallest distances, and then to do majority voting. So that's how in inference, yes, it's costly. Does it answer your question? No, you're welcome. Okay. Okay, so you can still think about questions. Meanwhile, I maybe wanted to mention for this afternoon, so we'll do some hands-on implementation of those machine learning algorithms using known softwares. To do the tutorial, you will just need a Google account, because we will use a Colab to do the hands-on experiment. So basically, you don't need to install anything on your computer, but you need to have a Google account. So I hope all of you have a Gmail. You just need a Gmail address to do that, and we'll share the tutorial with you. You will just have to run it and to edit it on your own drive, Google Drive. Okay, that's okay with you? So if you don't have a Google email address, please, during the lunch break, create one just for the tutorial. And we'll share this with you. And let's remind you that the afternoon session will start at 1:30. Okay. No more questions? So will you share the slides later? I guess we just need maybe with Ronald just need to ask Prof. Scarlett, right? It should be okay. We just need to confirm with our prof. Sure, we'll let you know. All right. So if you don't have any questions yet, we wish you a good lunch, and let's see each other back at 1:30 with your Google Gmail address, please. All right. All right, that's it. Thank you very much for your attention. Thank you. Have a good lunch break. Thank you. Bye.